Hello, welcome. I'm KR and we'll be exploring a new series of videos that will be a very light crash course to quantum computing. Today, we'll be exploring quantum states and qubits. Now, I want to assume to you that you already know what is linear algebra and complex numbers. Before answering what quantum bits are, we must ask ourselves, what is quantum? What does it mean to be quantum? If we think of quantum, we typically think of objects that are very, very small. This can be electrons, atoms, ions, photons, and many more very small things that make up the entire world, essentially. Now, you would see na they govern the very, very small world. And we can define quantum as this, essentially. Quantum can be thought as the smallest discrete unit of any physical property to do an interaction. Now, what does it mean in terms of examples? Let's say we have an electron right here. The electron wants to jump to the next level, but it cannot because it doesn't have the small required energy amount to do so. And in order to jump, it needs to be hit with the electron that has one quanta of that energy. And here we can see in this diagram, by being hit of this one quanta, it was able to do what? An interaction to jump. Now that way means to be quantum. Now let's go off to the topic of this matter, the qubit. The qubit can be represented as this equation right here. Now, this is a scary equation, so let's break it down to what it actually means. So, right here, this strange bracket sort of um enclosure to the zeros and ones here is actually called the bracket notation. This angle brackets is actually denoting some sort of vector. For this case, for the zero instead of ket, it's actually this certain vector. And same goes to the one. These two right here can be thought as the basis state of a quantum bit, because this is actually the off state and the on state of a quantum bit. Now, the state of the qubit is represented as this symbol right here, which is your psi. And psi is the linear combination of these basis states, this 0 and this 1. Now, if this is a linear combination, what does it mean? Why is it, why are these constants right here? What does it mean? These constants are actually probabilities, because in the quantum world, everything has a sort of probability. The probability of this off and on state should be equal to 1. And from that, we can calculate what is the state of the qubit right here. Now let's go through some interesting representation of a qubit. One way to look at qubits is to look at the Bloch sphere. We would understand these values in a while, but for now, this Bloch sphere essentially represents what is the current state of a qubit. For this one, if we have a 100% probability of 0, the qubit, the state arrow is pointing 0 right over here. If we have, for this example, have 100% of the 1 ket, it's actually pointing up in this qubit. Now, what does it mean right here, chat? To have the arrow pointing sideways, let's say for this one, for the positive ket. This corresponds to a superposition of the two. It composes both the position of 0 and the position of 1 at the same time. Now, the key properties of superposition is that the values here, the actual value of this state vector is kinda not really known until you do a measurement. But as it is right now, it's both alive and dead, up and down, 1 and 0. And until we do some sort of interaction, is that when we know what is the actual value this qubit holds. In a formal definition, a superposition is a state where both basis states exist, but we do not know what the actual value is. It's really unknown unless we measure it. What we do know is the probabilities of getting each basis state when we're gonna do that measurement. That is superposition right there. Now, the next one would be decoherence. Okay, what does this mean? When we try to look or poke around the actual value of the qubit right here, we're actually doing decoherence. It is the collapse of this superposition right here. Now, the positive plus right here, the positive ket, is not really significantly valuable as a sort of value when you try to measure it against our basis states, which is 0 and 1. But plus doesn't mean really anything for when you try to base this on 0 and 1 as your key, as your basis, kumbaga. Now, what is the actual definition of decoherence? It is the collapse of the superposition, measuring the state psi in the basis states 0 and 1 yields the following properties. It yields 0 with a probability of a squared and 1 with the probability of beta squared, collapsing the state. Now, these two properties are present in single qubit applications, but for multi-qubit computing, there's a third property that's very useful, and that is entanglement. Basically, entanglement is useful when you want to spread some sort of operation with multiple qubits. Entanglement happens with multi-qubit systems. They link calculations into multiple qubits and correlate their states, basically. And those three key properties govern the design and the um, creation of quantum algorithms and qubits right here. We won't get to a deep dive of the quantum mechanics right here, but these are really essential to understand to what is the usefulness of the qubit. And that's about it for this lecture.